Well, welcome to ChemCast 1.5. We are dealing with numbers, especially from measurement, and two topics that come up in dealing with that we're going to deal with in part one here. Part A is precision and significant figures. So when we're dealing with measurement and we're using our measurement tool, whatever it is we talked about like last time with graduated cylinders or rulers or whatever, the numbers that we can read from it is determined by the scale that's on the tool. So different tools have different scales. Even the same, measuring the same type of thing, they can even have different scales. And so the scale or the divisions or the markings or whatever you want to call it, it determines the readability. In other words, how many decimal places can you read from that tool? And one thing that we need to be remembering when we're using these tools is that we always need to include an estimate to show like when measurement lies between the scales or between the markings. Now you say, well, it doesn't always do that. Well, that's true, but the reported value from your measurement tool speaks to the precision of the tool for those that read your numbers. They know that that last decimal place must be an estimate between the scale on your tool. Right, so here you can see 50 and 60. So we go down to the ones place. So when it's between the lines, we can estimate to the tenths place. Or in this one, you got 6 and 8, so there's 7. So each of these is 0.2. Right, and again, you can estimate between those two. So if these are 0.2, then estimating between those two could be, to the hundredths place. All right, so the divisions here on the scale speaks to how good its precision is. And so when someone reads your number, it tells them how good your measurement tool was. All right, so not everything that we do in chemistry is a measured number, and so sometimes we have to do some calculations. Well, remember that the decimal places that we represent in our number comes from the measurement tool. Well, sometimes when we do calculations, you've all seen when they give us a screen full of numbers, simply by adding, subtracting, multiplying, dividing, we can't make it a better number. We can't give it more precision just by doing a little bit of math on it, right? So that always brings up, well, where do you round? What is the factor that limits the digits? And in math classes, you're probably just told, oh, go to 3 places or 2 places or 1 place or whatever, and you never really explained why. Well, here is why. It's because of the precision, and it's because of significant figures. And we'll talk more about that here in a minute, but basically a significant figure, or sig fig, or just SF, are digits that were actually measured. Yes, sometimes digits that we show in our measurement were not measured. They're just holding a place value, either to show that the number was really big, like a trillion, and you've got all those zeros at the end, or you've got, like a nanogram, right? Really small number. And so all those zeros out the front aren't measured. They're just holding place value to tell you an approximate size. Right? So the first one, in using precision, precision is determined by the smallest division on the scale. It's basically what we talked about a second ago, and one estimated digit. So this is the part that people tend to forget, estimating that digit. Okay, when you're looking at a number, sometimes you're given numbers and you have to determine what the precision of it is. It's just simply very easy, the rightmost digit or place. Well, sometimes those numbers are big, like a billion, trillion, those kinds of things, and not all of those digits are measured. So what we do is sometimes there's a line above a 0. That's the end of the precision. If you see a line above a 0, that's the end. Or just simply the rightmost digit. Okay, actually the rightmost non-zero. All right, so sometimes those zeros just hold place values and they're not really measured, and you'll see examples of that here in just a second. Okay, so basically, the tool that you have, the more markings on your tool, the more precision it has. Well, here's 2 examples. Right? Here's a scale that's down to the ones place. Here's a scale that's down to the tenths place. And so these markings on here give us better readability. This one we could estimate, maybe 0.4. Now this black line and this black line are duplicates of each other. And so when you see it's actually more than 0.4, in fact, we have to make this estimate in here as to where this line falls. So we would say something like 3.45, 3.46, maybe 3.47. Again, that last place is an estimate. And so there's going to be some wiggle room in there. There's not one right answer because everybody might see it just a little bit differently. Okay, but you got to estimate that last digit. And so the more divisions we have, the better our precision is. In talking about precision, we can see some examples here of what we're talking about. But when we're looking for what is the precision of the number, precision is the rightmost non-zero integer or to the digit that has a line over the 0. All right? And so we can see then that if there is a decimal, then it's just simply, easiest case, all of it, last digit of the number. So easy. So you can see in these first set here, it just becomes very, very simple. And so let me switch over here to a pen. And so we have the thousands place, we have the hundreds place, it's got a decimal, so this is the thousands place, it's got a decimal, so it's the thousands place. I'm sorry, this was a 10,000s place. It's got a decimal, so it's thousandth, decimal, so it's got the thousands place is the end of the precision. Over here, where we don't have any decimals except for right here, so if in that case, we know that the very last digit then is the end of the precision, and so that would be the ones place. Now these others, we have to look at this other line here that says it's the rightmost non-zero integer or a line over a 0. So this first number does not have a line over any zeros, so it must be the rightmost digit. So the precision of the instrument used to measure this number was only good to the hundreds place. Because this one has a line over it, the tool used to measure this number is good to the tens place. Here, this instrument is good to the hundreds place. Now there's no line in this one, so this particular tool was only good to the thousands place. It doesn't have divisions for the ones place or the tens place or the hundreds place, so it was only good to the thousands. This one was good to the 1, this one was good to the 10, this one is no line, so it must only be good to the hundreds place. Alright, so sorry about that. I hope that didn't hurt your ears too bad. So that was precision. Okay, that's if you're given a number, you know how good the tool was based on that method right there. All right. So if there's a decimal, very last digit. If there's not a decimal, it's the rightmost integer, or if it's got a line over the top of it. All right. So two sig figs. Significant figures are number of digits that are read from a measurement. Okay. So when you record a number, how many digits you actually record from that measurement is the number of significant figures. And remember, sometimes we have extremely large numbers or extremely small numbers where the zeros are just holding place and they're not actually measured. So how do we determine how many significant figures are in a number? We start with the leftmost non-zero, and it goes until the precision runs out. Pretty easy. Leftmost non-zero and go until the precision runs out. Okay, so here we go again, and what I've done on this slide is it's the exact same numbers from the previous exercise with precision, so I just went ahead and threw up not actually upchuck, but I placed up there the markings there for the precision that we picked up in the last time we saw these numbers and dealing with precision, so that we didn't have to do that again. All right, so significant figures starts with the leftmost non-zero integer and goes until the precision runs out. All right, so I've got my little handy dandy pen here, and these are not integers. So if you just think about all of these zeros here at the front will never count towards significant figures because it's the leftmost non-zero integer. All right, so that means it has to be 3 until the precision runs out. So this has 2 significant figs. All right, here till the precision runs out, that's 2. This one is 2. Here we got 3. All right, here we've got 3. All right, so the leftmost non-zero integer until the precision runs out. Leftmost non-zero integer until the precision runs out. All right, same with this set over here. I'll go ahead and throw up where the precision runs out. Throw up. There you go. All right, so the leftmost non-zero integer until the precision runs out. Leftmost non-zero integer until the precision runs out. Leftmost non-zero integer until the precision runs out. Until the precision runs out. Non-zero integer until the precision runs out. All right, so that's pretty easy. All right, so then we can say that this one has 3, this one has 4, this one has 2, this one has 3, this one then has 5. Look what that decimal does. All of these are the same number, but because of the different precisions, gave us different significant figures. This one was 2, and this one was 3. So you can see that the precision of the instrument produces more significant figures than tools that have less significant figures. So precision is important in dealing with your measurements. The more precision, the more significant digits, significant figures you get. All right? Well, there might be asking yourself, why in the world would we need to ever know when precision runs out or how many significant figures are in a number? Well, that's what the next ChemCast is going to be about. And it's when you do calculations, you have to use either the precision or you have to use the number of significant figures. So we'll check that out the next time we meet.